this one. So an electric field of 3,000 volts per centimeter. So we have an electric field, 3,000 volts per centimeter. May cause the air to ionize and allow electrons to jump from one surface to another, causing a spark. An electrostatic charge is produced on a student walking across a rugged floor. He reaches for a doorknob. Assuming the electric field of 3,000 volts per centimeter, determine the electric potential difference required between the finger and the doorknob to produce a spark when they are separated by 1.2 centimeters. So we have a separation of 1.2 centimeters. And we're finding delta V. So nothing too complex here. Just an example of how to use this basic formula. So if we're solving for delta V, then delta V is equal to E times D. And we can leave it as centimeters because then we can just cancel centimeters out since they're both the same. So we'll have 3,000 volts per centimeter times by 1.2 centimeters. So we end up with 3,600 volts. In sig digs, 3.6 times 10 to the 3. Okay, this one is a little bit more complex. So an electron, okay, let's just stop there for a second. Data sheet. Do you need one?
No, I have it. It's just in my binding.
So let's look up our information about electrons. So we know that it has a charge of 1 e, which is an elementary charge, and we know its mass at our particles chart. Okay, so let's just put down first what we know about our electron, because this is our particle we're dealing with. So my electron, it has a charge of 1 e, which is 1.6 times 10 to the negative 19 coulombs. Pardon? Yes. Thanks. And then we're told its mass is 9.11 times 10 to the negative 31 kilograms. Now it says it has a speed of 5.8 times 10 to the 5 meters per second. So that's our initial speed because it's going to change. So VI is 5.8 times 10 to the 5 meters per second. When it enters a set of parallel plates, so let's just draw parallel plates to get an idea of what's happening here. So let's say it enters here. When it says in questions that a particle enters the plate, it needs to enter from the side, okay? So it's going to be attracted to the positive, right? So, but it's not going to just go straight up because it has a horizontal motion too. So what's going to end up happening is it's going to kind of go up in a parabolic motion. Kind of similar to, in a way that you think about like a projectile being launched. Okay? So we have our electron, it enters the parallel plates at this velocity, or speed. If the electrical potential difference is 140, what is the exit speed of the electron? So as it goes, and I guess this implies that it's going to exit, or something like that, go out. What's it's going to... this is its VI. Oh, we're told it's VI. Sorry. And the question's asking us what's its VF as it leaves. So we need to think about it as acceleration. Okay? Okay, so we're looking for VF. Oh, not zero, question mark. Goodness. Okay. Oh, and we know our delta V is 140 volts. Now, we don't know distance and time, so we don't have anything else but VI to do an acceleration formula, right? Like for acceleration formulas, you need VI or VF, D, T, things like that. We don't have that. All we have is VI. But, we have mass, we have electrical potential difference. So what we're going to use is change in energy. Change in energy. So the way we're going to approach this is we're going to find EK final. No, we'll just go, let's go, we're going to have EK equals half mv squared. Okay. We are going to use that, we're going to go delta E is equal, delta EK is equal to EK final minus EK initial. Yeah, this will be our EK final. And we're going to get delta EK from delta V equals delta E over Q. So it's like we need to find this in order to get this. But in order to get this, we need to get this. And in order to get that, we need to do this. So this is like, this will be step 1, and then step 2, and then step 3. So when you know that an object's accelerating, but you don't have acceleration data, think, what else do I know? And if you have your delta V, you can find delta E. So let's do the first one. So number 1, our first step, we're looking for delta E. So we go delta V times by Q. So that's 140 volts multiplied by 1.6 times 10 to the negative 19 coulombs. So we get 2.24 times 10 to the negative 17 joules. So that was my change in energy. So I'm going to apply that to, that's kinetic energy because it was moving. So now step 2. Step 2, I'm going to use delta E and go EK final minus EK initial. I want to solve for EKF. So let's rearrange to solve for EKF. So that's delta E plus EK initial is equal to EK final. So I can expand that to saying that's delta E plus half m VI squared is equal to EKF. Now I can put in my actual data from what I have. Am I going too fast? Pardon? Okay. Are you doing okay, Matt? All right, so I know my delta E, because we just solved for that, right? Yeah, we did. So that's 2.24 times 10 to the negative 17 joules. And I'm going to add half times by 9.11 times 10 to the negative 31. This is going to be a lot of fun calculator punching, right? Lots of scientific notation. Times by my initial velocity that I was given, 5.8 times 10 to the 5 meters per second. Now make sure that that value is squared. So if you're doing it all at once in your calculator, I caution to use brackets. Use your brackets. So try putting that in, see what you get. Should get 2.25 times 10 to the negative 17. So, if you wanted to as well, you could first calculate this out, which is 1.53 times 10 to the negative 19, and then add this and this together, if you prefer. Okay, but you should get 2.25 times 10 to the negative 17. So then the last step is to take that final kinetic energy and solve for VF. So your VF is the square root 2ek over m. And that's ek. Remember our mass of our electron, we know. So when you punch it in, you should get 7.0365 times 10 to the 6 meters per second. So for sig dig, 7.04.